Okay, I will explain about MECHA, our paper, which is proposing a multi-thread and efficient cryptographic hardware access. So the first, I will explain about the introduction, which is define which problem to be solved, and next I will explain about our implementation design, which contains Unix domain socket and multi-thread architecture, and then end it with result and conclusion with the experiment that we have done with MECHA. So now the problem to be solved is the necessity of this research that the number of processor available usually in an environment is less than the number of application, which usually the cryptographic processor is used together by the different application, and sending each cryptographic operation request takes time, and more requests means it takes more time. Now the multiple requests to crypto processor needs to be managed, and intermediary application is needed. Usually we have crypto server or crypto proxy, and intermediary application will increase the risk of bugs and security issue. Now in centralized crypto request management, once the central is down, for example, we have crypto server application which is failure and it is done or get compromised, all of the requests will fail until the system is recovered. And this another one is that the complicated integration or even not portable integration of various type of crypto libraries should be easy, and we have to make it scalable and portable. And the research scope of this MECHA is a multi-thread API that connect as alternate function of crypto algorithm implementation. We have a crypto library here. This is the application which connect to using connect to other instance using protocols such as HTTPS, CoAP, MQTT, LLM2M, Profinet or Modbus, TCP, etc. will use a crypto library which is used widely by different application, which has a custom function which is called usually crypto alternate function. In OpenSSL is usually crypto engine, and this defined crypto function is modified by the vendor to match with their system such as crypto hardware. And then the research environment overview of this paper is that the application usually encrypt data using API that communicate with server app, which will manage the traffic to FTDI. So we have one server thread here created by the first application that use crypto library, and then this is our MECHA crypto API that create this server thread, providing a bridge between the other application too into the same cryptographic hardware. So this server thread is created the first application, and then this will provide interface between these two instances, and this can be implemented on Windows, which has Unix domain socket equivalent, Mac, and of course Linux. And the research objective is that we have to integrate the current API as alternate crypto function to the existing crypto library, and we have to identify the crypto requests and distinguish an address of the crypto requests from different API instance. We collect the multiple requests from multiple API, and we do the scheduling, and then we will send the multiple crypto requests at once. And we also need to experiment with the hardware interface to get the performance benchmark. Now, for the implementation method, we will use and utilize the existing design, which is Unix domain socket and server thread, client thread creation, transceiver thread, and the interface, which can be replaced by anything, but in this experiment we use SPI. Now for the inter-process communication is a set of programming interface that allow the programmer to coordinate activities among various program processes. For example, we have process A and process B will interact each other and exchange information, usually using signal such as in kernel or TCP, UDP, which is used by internet and others. And also in this research we use Unix domain socket, which it's in our opinion is the best to use in this case. And there are also other technique like message queue, pipe, shared memory, message passing, and etc. Just like internet socket, this Unix domain socket is meant to communicate with one socket, and other process can communicate with each other. For example, here we have client server model. The socket is bind to address and listen for connection. The client is connect and read and write the data between the server and client. And thread definition is a basic of CPU utilization. It consists of program counter, stack, and set of register. And there are also thread ID. And this one is single thread process, which has one code, data files, and register stack. But in multi-thread, code data files is one, but the register and stack is different for each thread. So in traditional process, it's only one program counter, and multi-thread is multiple program counter, stack, and set of registers, so it can share common data and structure such as opening file and others. But in traditional process, it's only one sequence of instruction at a time. Now, in multi-thread server architecture, thread is very useful in client-server architecture. For example, in word processor or even web server, when the client requests for some connection, the server will respond and create a new thread to process the client request, and the server will wait for another additional different client request. Now, this is the overall simplified of our architecture. We can have 6 app and 6 API instance. For example, this star one is the API that is first launched, and it will create the server thread. And once other connected, a client thread will be created for each of these application, and then will be managed. Will send the data into send queue. The receiver thread will pass it and manage forward into interface and the crypto core, and then the response will be in queue and then sent back to the corresponding requesting application. Now the component and function for the app is that the app is in here is the application that use our API, the MECHA, and then is our server, our API, our proposed API. There is server thread which manages the connection between application and Unix domain socket that created by the server thread, and the client thread that created by server thread each time the new application is connected to the socket. So one thread for each application connected and will stay alive until connection closed. And there is also a transceiver thread which is dedicated for sending and receiving between the server and crypto hardware. There is also a send queue and receive queue will buffer all the encrypt and decrypt data requests from the hardware, and any client can put the data in this queue with the socket number as header. This is to avoid the data being swapped within each other. And in receive queue, any client can take the data according to the corresponding socket number. And this is the server thread communication flow in MECHA. There are a server thread which bind and listen to an address, and application one start and connect to the server thread. Server thread create a client thread and exchange data. This is almost the same like the web server communication. Now this is the MECHA detailed overview. We have customer application, crypto libraries such as OpenSSL, TLS, and so on. We have encrypt, decrypt, hash for each block, cipher, function, and then once the first application connect, it has the socket number. It's used to connect to UDS, send and receive. Then in server thread, one connection is one thread, and when the client has data to be sent, it will enqueue into the queue, send queue, and then the transceiver thread will monitor this, while client thread will monitor from the other side. So transceiver thread will dequeue and enqueue the response once it passes from the crypto chip hardware. This can be SPI, UART, and other protocol, and this is very modular and portable. For example, here we have 15 megahertz SPI connection, which using SPI to XX library, or we can change to UART to XX library or different another interface. Now, this this features multi-thread data handling, it has model interface, and supported in the multiple platform. Now we will dive into the flow of single cryptographic operation requests from start of single flow application request and connect to UDS. If it's success, it's continue. If not, it will create new thread, and the thread will assign connection to thread pool, and client thread put connection socket number along with the PDU into the sequence, into the send queue, and then the transceiver thread reads the CSN and then pass to video crypto hardware. After this response is received in transceiver, we'll put back to the receive queue, and the client thread will monitor and take the data that corresponds to their own connection socket number if it's matched, and then it will send the video result to application using the BTLS interface. This is the template of testing how we call the MECHA. We start the protocol with user SPI. We initialize value. This can be any value. This is just an example of PDU that we use in our project. And we have add value, add this payload, and then it's sent. Now using PDU trans receive, it was automatically sent, and each sent data will be automatically processed immediately without waiting, because this is multi-thread. And after receive, it will print the buffer and then close the protocol. And this is the simple usage log. We can see this is a shared library test from PDU. We see that the client trying to connect, but no, not yet. And then we start the SPI, server started, waiting for connection, the send and receive thread started, then the client tried to connect again, it's connected, and then the server gives the 23 as the socket ID, and it's connected. It will create a new thread with the same socket ID number, and then immediately this client tried to transceive and get status which is okay, and then when the payload send and receive is the same. This is an example of one application, and this is the example of 3 applications together connected. In this case, the server thread is started by the A instance. We have BC, ABC, which each of these has thousands of loops, and each loop has 10 bytes transfer, which is all of the 1000 loops is valid. This happens together at the same time without any mismatch data between each other, which is in this case is random. And our experiment result that in MECHA, the context switching API with 5 instances takes 3.86 seconds, while in MECHA 1.95 seconds. And then after we increase the application instance that runs together by sending 100 data together, took the same time at 10 instance, but in context API instance it takes 5.91. And then after we scale up into 70 and 80 application running together, the difference becomes bigger, and the MECHA increased this efficiency up to 83%. So while in MECHA it took only 6.44 for each 80 application finish their cryptographic request, in context switching API it took about 37.56 seconds to complete all of the cryptographic requests. So with this experiment, we can conclude that the MECHA was able to handle multiple cryptographic requests at the same time with limited number of crypto processor, and it can collect and send multiple cryptographic operation requests at once for time efficiency up to 83, and can manage requests to crypto processor without needing intermediary application, which is the server thread is built by its own API thread. And then this is the decentralized crypto request management, can be requested by anyone, any application that has permission for the cryptographic hardware. And this MECHA has high portability and easily integrated with that hassle-like software crypto module. We conclude that MECHA is feasible and practical to replace the conventional context switching API designed for crypto hardware interface, and offering a faster, more efficient solution for managing multiple cryptographic operations simultaneously in one cryptographic hardware. Thank you.